Class 11th Chemistry, Unit 3, Classification of Elements and Periodicity in Properties, and in this video we will discuss about periodic trends in atomic radius and ionic radius of elements. First come to atomic radius. Actually, atomic size is expressed in terms of atomic radius, or we can say atomic radius also represent the atomic size. And finding the size of an atom is a lot more complicated than measuring the size or radius of a ball. Why? Two reasons are there. Size of an atom, that is radius of an atom, is very small, and generally this is in this range, 10 to the power minus 10 meter. Second reason, the electron cloud surrounding the atom does not have a sharp boundary. So the determination of atomic size cannot be precise. Therefore, an estimate of the atomic size can be made by knowing the distance between the atoms in the combined state. For non-metallic element, we use the word covalent radius because non-metallic element bound by forming covalent bond. Okay. Now, what is this covalent radius? It is half the distance between two atoms when they are bound together by a single bond in a covalent molecule. For example, the bond distance in the chlorine molecule, that is Cl2, is 198 picometer, and half this distance, that is 99 picometer, is taken as the atomic radius of chlorine. You can see this diagram. This is one chlorine atom and this is the another chlorine atom, and these two chlorine atoms make a covalent bond by overlapping of their electron clouds. This represents the overlapping or formation of a bond. This is the nucleus of one chlorine atom, this is the nucleus of another chlorine atom, and the distance between these two nuclei, this is called internuclear distance or bond distance. And half of it, it is from this to this. This is taken as atomic, this is taken as covalent radii of the chlorine atom. And this is also referred as an atomic radius. Okay. For metals, we use the term metallic radius. It is taken as half the internuclear distance separating the metal cores in the metallic crystal. For example, the distance between two adjacent copper atoms in solid copper is 256 picometer, hence the metallic radius of copper is assigned a value of 128 picometer, which is half of this. Again, you can see this diagram. This, if we consider any metallic crystal, this is one metal atom, this is the another metal atom, okay, and they are bound by a metallic force. And this distance from nucleus of this atom to nucleus of this atom, this is the internuclear distance, and half of it, this one, this is referred as metallic radius. Is it clear? Generally, atomic radius refer to both covalent or metallic radius depending on whether the element is a non-metal or a metal. Simply we can say covalent radius and metallic radius both are regarded as a atomic radius. Wonderwall radius. It is half the distance between two adjacent atoms when they are not bound together by any bond, and it is greater than covalent radius. Now again have a look to this diagram. This represents one chlorine molecule, this represents another chlorine molecule, and this chlorine molecule is formed by overlapping of these chlorine atoms. We can say in between these two chlorine atoms, this is a bond. In between these two chlorine atoms, this is a bond. But this chlorine atom and this chlorine atom is not bound by any bond. That's why the distance from this nucleus to this nucleus, this is again also known as the internuclear distance. Okay, but half of this internuclear distance is known as Wonderwall's radius. Okay, and this Wonderwall radius is always greater than the covalent radius. For this chlorine, you can say 180 picometer is the Wonderwall radius, while covalent radius is only 99 picometer. Variation of atomic size in a period. Atomic size generally decreases across a period from left to right. Now, what is the reason? It is because within the period, the outer electrons are in the same valency shell and the effective nuclear charge increases as the atomic number increases, resulting in the increased attraction of electrons to the nucleus. In this table, atomic radii of second period element and third period element are given. This is atomic, we can say elements of the second period element, and this is the atomic radius of these elements. You can see clearly this is decreases if we go from left to right. In the same way, these are the third period elements, and this represent the atomic radius of these elements. Again, this is a decreases if we go from left to right. We can also plot a graph between atomic radius and atomic number, and this is a decreases in a period as the atomic number increases. Now, in this case, actually after the fluorine and chlorine, we can say after the halogen, noble gases are there. But atomic radius of noble gases are not used to compare with other elements. Why? Because atomic, this is the reason, atomic radii of noble gases are not considered here. Why? Because for noble gases, Wonderwall radii is calculated, and Wonderwall radii is a non-bonded radii. While for these remaining elements, we use the covalent radius or metallic radius, and covalent radius and metallic radius both are regarded as atomic radius. That's why Wonderwall radii are not compared with the atomic radii. Variation of atomic size in a group. Within a group of the periodic table, the atomic radius or size increases regularly with atomic number. This is because down the group, the principal quantum number, that is n, increases. Or in another terms, we can say number of cells increases down the group, and valency electrons are away from the nucleus. There is also the one more reason. Also, energy levels shield inner energy levels. Okay, inner energy levels, or we can say inner electrons, shield the outer electrons from the pull of the nucleus. So effective nuclear charge is decreases. Consequently, the size of the atom increases. Again, you can see these are the elements of group 1, and this is atomic radius. This is continuously increases down the group. These are the elements of group 17. And again, you can see atomic radius is continuously increases down the group. And in this plot, again, you can see same thing. This is between atomic radius and atomic number. As the atomic number increases in a group, atomic size or atomic radius increases. Clear? Now come to ionic radius. Ionic radius is the distance from the nucleus of an ion up to which it has an influence on its electron cloud. And as we know, two types of ions are there. One is cation and another one is anion. And cation is formed by the removal of an electron from an atom, and anion is formed by gain of an electron by an atom. The ionic radii can be estimated by measuring the distances between cations and anions in ionic crystal. This is a simple one part of ionic crystal in which cation and anions are represented. And from this to this is again internuclear distance between cation and anion. And with the help of this, we can find out that is radius of cation and radius of anion. In general, the ionic radii of elements exhibit the same trends as the atomic radii. It means if you go from left to right in a period, ionic radii is also decrease. And if you go from top to bottom in a period, ionic radii increase. Okay. Now, size of cation. A cation is smaller than its parent atom because it has fewer electrons while its nuclear charge remains the same. So effective nuclear charge increases. For example, atomic radius of sodium is 186 picometer compared to the ionic radius of 95 picometer for Na+. You can see this diagram. This is sodium atom. Electronic configuration is 281, and in this case, electrons. How many electrons are there? 11 electrons are there. And how many protons are there? Again, protons are also 11. When sodium ion is formed, sodium atom lose 1 electrons. That's why in sodium ion number of electrons are 10. But number of protons remains the same. That is 11. Now we can say in this case number of electrons are less. That's why effective nuclear charge is more and size is decreased. Moreover, we can also say in this formation of cation, this outermost shell is completely vanished. That's why size is also decreased. Size of anion. Size of anion will be larger than that of the parent atom because the addition of one or more electrons would result in increased repulsion among the electrons and a decrease in effective nuclear charge. For example, the ionic radius of chloride ion is 181 picometer, whereas the atomic radius of chlorine is only 99 picometer. In this diagram, you can see this is chlorine atom. It contains 17 proton and 17 electron. And when it gains 1 electron to make or to convert into chloride ion, number of electrons are increases, but there is no change in number of protons. Okay, that's why we can say now same number of protons are attracting the more number of electrons. That's why effective nuclear charge is decreased and size is increased. Isoelectronic species. Two or more species with same number of atoms, same number of valence electrons and same structure regardless of the nature of elements involved are called isoelectronic species. For example, O2 minus, F minus, Na plus, Mg2 plus have the same number of electrons, that is 10. The radii would be different because of their different nuclear charges. More the nuclear charges, smaller the size. Okay, just compare. These are the species, all contains 10 electrons. Now if we compare their nuclear charge means number of protons. In oxygen, number of protons are 8, in this 9, in this 11, and this is 12. That is, in Mg2 plus, more number of protons, that is more nuclear charge. That's why its size is smallest among these species. Is it clear? Now there is one question. Which of the following species will have the largest and the smallest size? These are the species given to you. Now again compare their position in the periodic table. If you compare, this is magnesium and aluminium is the right side of the magnesium. And as we know, if we go from left to right, that is across a period, atomic radii decreases. That's why this This is magnesium is larger than aluminium. Okay, you can say this is magnesium is larger than aluminium. Okay, now if we compare their size with their ions, we can see among isoelectronic species, the one with the larger positive nuclear charge will have a smaller radius. This Mg2 plus and Al3 plus, both are isoelectronic species. Okay, but in case of Al3 plus, more number of protons are there. There is more nuclear charge is there. That's why this is smaller. Al3 plus is smaller. Now, if we compare these data, we can say which one is largest in size, magnesium, and smallest, that is Al3 plus. This is our answer. Largest species Mg and the smallest one is Al3 plus. Okay student, subscribe my channel to get the new video of this chapter.